Welcome everybody, my name is Chalmer Lowe. We're going to go through real quick some of the install instructions, and then we'll get through and start doing some expectation management, those kinds of things. Most of you have probably done the install instructions already, so I'm just going to cover those briefly. A couple tools we want to have on our systems. I tend to prefer using a tool called Conda to help me do package management. Some specific libraries that we're going to install, we'll walk through those. We'll go through how we test for installation and talk a little bit about why we're doing things with this way. One of the things that I often recommend, read all the steps ahead of time, get a sense that you understand what the steps mean. Some steps may say install thus, and turns out you already have it installed, so you may not have to do that. For this tutorial, I highly recommend using Conda as a package manager because there are some libraries that are kind of sucked into this process that are not necessarily Python libraries, so some Python package managers may not be real good for this. Conda has a virtual environment manager to help manage your virtual environments, and we'll talk a bit about what that means. The material for this has been tested using Conda, but it has not been tested with pip, it has not been tested with virtualenv, etc. If you already have Conda installed, you can test that by typing Conda on the command line. And if you get something back that says usage Conda, you're good. If not, the instruction should walk you through it. For this course material, we're using Python version 3.x. When you say Python equals 3 in one of the commands we'll do in a minute, it'll give you the latest version of Python. From my experience, the most common problem that I see when people start to do this is they miss a step, right? Our eyes tend to glaze over and we miss things. So if you have a problem, scroll back, check to see if you've done all the things. If not, we have a set of mentors in the room and myself. We can walk around and help you, especially during the part where we do exercises. All right. There are a set of instructions for doing this in Windows and Mac and Linux. You can confirm whether Conda has been installed by doing Conda or Conda list.
Chalmer,
yep.
I just caught something. Can you turn your microphone on, please?
Awesome.
So we get it on the recording. Thank you.
This is high tech, guys. All right. Next. All right, so let's talk a little bit about what we're doing when we're installing Python and some of the other things. You're going to make a directory called stats. You're going to change into that directory, so now you're inside that folder. And we're going to create a virtual environment. At the bottom of this material, I have kind of a write-up as to why virtual environments are important and how they can be useful to you. And I'll leave that up to you to read it. But the big picture for virtual environments and why you might want to use one is that it creates a sandbox. Some of you have Python already installed in your computers, and you maybe use it for work. And you don't want to corrupt or mess up your existing version of Python or your existing libraries that use with Python. So the virtual environment makes a sandbox. What we do goes in the sandbox, and it doesn't interfere with anything that happens, right? Once we've made a virtual environment, we have to activate it. And if you've activated a virtual environment, you're going to see these little parenthetical off to the side to say you're now using that virtual environment and now using the version of Python that you installed for that environment. And then next, we can say Conda install, and you can tell it all the libraries that you would like to use. In this case, we have 5 main libraries that we intend to explore. All right. Once you've installed those, we'll type Jupyter space lab, and hopefully a lab environment will open up. If you do not have one, let us know, and we'll get you taken care of. You can kind of raise your hand. I'm going to pass out some stickies as well in a little bit. All right. Next, we have class material. It is up on GitHub. I'll put the links back up for those in a second. You guys can go look for that. All right. As we go through the process, you'll see these green Post-it notes in the material. All the stuff I want you to do basically stops there. If you want to keep reading, you can go ahead, but you can typically stop wherever a green Post-it note is. For those who really want to know more details about all of these things, at the bottom of this lesson, I have a big picture description of why we use virtual environments, what is Conda doing, why are we using it, and all that stuff. And so you can scroll through and read all of that content at your leisure. We're not going to go into it. All right. So with that in mind, going to walk you through a little bit about kind of how this class itself is going to play out and the types of things that we want to do. All right. First off, I appreciate PyCon, my family, friends who suffered through me trying to get this material ready, my company that helps to get me here, Booz Allen Hamilton, the PyCon Tutorial Selection Committee, the mentors who are here in the room who are going to be helping you guys, and especially you for being willing to come out and go through this statistics and probability exploration with me to give you an idea of what to expect and what not to expect, right? We'll do an overview of some probability and statistics. So it's a tough word, right? It's hard. English is tough. We're going to do an overview of probability and statistics principles and techniques. We will have some snippets of Python code. I'm going to warn you right now. The code that Chalmer wrote for here should never be used in a production environment. The things that I wrote are more to demo principles, to give you an idea of how things work kind of under the hood. They are not for true statistical analysis, and I'll prove it. I'll show you why. There's going to be plenty of opportunities for you to level up your skills. We will have exercises that you guys can walk through, and we'll give you a certain amount of time in this tutorial to work on those. Myself and the mentors will help you. I will highlight a few of the gotchas to look out for, things that you might be experiencing as you go through this journey on your own, when you get back to your house, etc. And we're going to provide some resources to help you continue your learning journey. When you go home, what are some good books to read, or what are some good things to look at, etc. So what not to expect. If you think this through, a typical college class is about 40-some-odd hours of sitting in a lecture hall, lots of homework in between sitting in lecture halls. We have 3.5 hours, and if we bring biology and taking breaks and stuff into this story, we have about 3 hours, right? So you're not going to get a whole lot out of this. My hope, though, is that you will get a flavor, and that flavor will drive you to go home and keep learning. You are not going to get out of Chalmer robust industrialized code. We spoke about that. And in terms of deep dives, we're not going to have the time. So some folks may ask some questions like, hey, I want to know a little bit more about these types of distributions and how these are related to that. We're probably not going to have the time for a lot of that. We could have maybe conversations about that outside of this. I really want to give you guys this nice high-level overview. In terms of logistics, pair practice is used in some tutorials because working closely with a partner helps you kind of identify what's going wrong and help each other out. I'm not going to force that upon anyone. If you want to work with someone who sits next to you and say, hey, why don't we work on the code together, or why don't we work through these exercises as a pair, I'll leave that up to you and your level of comfort. We're going to distribute out some Post-it notes for you. When you get to the end of a period of exercises, you put your Post-it note at the top of your monitor so I can look out. When I see a sea of green, I know it's time to kind of move on. If you run into a problem, you'll have a red Post-it note that we'll hand out to you. You put it on your monitor. Myself or the mentors will look out and go, oh, red Post-it, and we'll come to you, right? So you don't have to do this whole embarrassing, hey, I got a problem thing. There will be a survey, and I'll get you the link to that later. I really want to get your feedback, okay? So how do we get the most out of this experience? I love this picture, and let me zoom down so you can kind of see it. The top, and I apologize, it's small font, it says, how do you actually learn any new programming concept? By changing stuff and seeing what happens. One of the cool things about Python is that you can try something, run it, and see what happens. You go, wow, that was cool. Let me change this number, or let me do this thing. And you run it again, and you get an instantaneous kind of response. So I heavily encourage you, play with things when you do an exercise and you get done a little early. Try and go back and do it again, tweak something. You're going to have questions that might come up like, hey, Chalmer, what if, or what will happen if we do this? And I love to hear those questions. Those are great. I will caveat that, though, with I also love to see folks have that question in their head and they go try it themselves. Because sure, I can demo it for you, but man, how much fun and excitement it is to try it and see some cool response. Some people say, well, I don't want to break anything, and I don't want to do it wrong. And that's a legit fear, so I'm not going to minimize that. But generally with Python, you're not really going to break much. And if you do, you can kind of reboot. And often if you do, quote unquote, break a thing, there's going to be some error message, and you're going to skim it, and maybe it's confusing, but you're going to see new words, new terms, and you're going to start to learn things. Because those error messages, as scary as they might look, will often teach you things, especially when you see them over and over again. So try not to be scared. There's a couple other things in here, and I'm not going to go through them in the interest of time, but they're there, and they talk about the psychology of learning stuff. But this quote here is kind of neat. Being a programmer basically requires you to deal with these extended periods of feeling like a complete moron, punctuated by very brief periods of feeling like a genius, right? That's my life every day. I'm standing up here trying to teach you guys a thing, but most of my life is, I don't know how to get my code to do this thing, and I don't know why. And then all of a sudden it works. And I feel like that guy on the Titanic, right? And I feel great. And then my boss is like, we'll solve this other problem now that that's done. Like, suck. Okay, so let's get rolling. Let's talk about statistics. All right, so this is kind of the main meat of the thing. I'm going to disappear behind the podium and grab those Post-its and have one of my colleagues pass them around. All right, and then I'll come back. I'm still here. Voila. All right. Everybody gets one green, one red. Not one pad, one green Post-it, one red Post-it. You don't know what he's going to do. All right. So let's get started. This first conversation is going to talk about statistics, right? And what we can do with that. And then a little later on, we're going to move into probability, okay? Our main goal right now for this first little bit is to understand, some techniques for counting things, to determining what the minimum value is, maybe in a data set, figuring out what the maximum value is. And then we will look at these things that we call central tendencies. The fast version is what's the average? And we'll explore different ways to look at that. And then we will talk about, well, how widely does stuff kind of deviate from that average? Is my data really spread out or not? Okay. Let me try and blow this up a little bit, maybe. Okay. We're going to look at the data, and we're going to look at these techniques and these processes through a couple different tools. We're going to start off with some simple data sets, just a couple numbers so we can kind of visually see what the thing is. We will then go through a little bit larger data set, a little more sophisticated. We're going to have some hand-developed code. That's Chalmer's. Do not use this in production code. And then I'm going to walk you through a couple of standard libraries that have some functions that do what my code does, but does it way better. All right. To kind of get us in the right frame of mind, I'm going to use that big data set that I mentioned. We'll look at it, and we'll display it on the screen in a graph, and then we're going to use tools to kind of figure out what some of those data points are, okay, by hand, as it were. All right. So let's pretend I'm a manufacturing plant, and every day I produce a new batch of stuff. On some days, my machinery is well-tuned, and the number of batches that I produce, or the batch that I produce has very few defects in it. But other days, my machinery is starting to fall apart, things are breaking, and all of a sudden, I get larger quantities of defects. So I may want to track these on a day-to-day basis. All right. So I have this data, and it is this number of defects. I purposely kind of organized it so it's kind of bigger numbers at the top, smaller numbers at the bottom. They're not quite sorted, but so we see some things like there's a 99, there's a 52, there's a 42. At the bottom, we have some 2s and 3s and 4s. I don't know, there's like 208 or some odd numbers. We'll figure that out. I will warn you, we're not going to do a deep dive into Matplotlib. I'm going to gloss over this real quick. I just want it to do a graph, but I use Matplotlib here to import some capabilities that will enable me to make a very basic plot. I also have a tool called the counter tool, and we'll talk a bit about it in a minute, that's going to help me count things. And now I want to make a simple histogram, a simple graph. What we're going to do is try and start off by making this display, and we're going to use a tool called most common, which is found in the counter object, and you'll see how that works out. All right, so I start off by taking all of those values that I had, number of defects, and I drop it into my counter object. And that's going to produce a thing that looks like a dictionary, but it's not quite. And so I call it defect counts. And then I say, all right, show me the 5 most common values that occurred in all of my number of defects. So we run that code. And so the number 8 showed up 24 times. The number 6 showed up 24 times. And the number 7 showed up 18. All right. I mentioned that counters look a little bit like dictionaries. There's 2 nuances that you should know. They have this kind of extra method that we just saw called most common that allows us to find out what are the most common things. And I can tell it I want to see the 2 most common items, and it'll give me that. Or I can say I want to see the 5 most common items, and it'll give me more. Right? But one other nuance that is fun is that if you've ever played with a dictionary and you try and access a value that doesn't, or access a key that doesn't exist, your dictionary will vomit on you, and it throws up this little error and says, hey, you tried to look at something that doesn't exist. Counters are cool that they don't do that. If I try to access the number 77, which is not in my defect count, it goes, that's fine, and it just gives me back a 0. If I try and access a number that does exist, like an 8, it'll look into the counter and go, oh, there was a 24 stored there, and it'll give me back a 24. So this is kind of cool, and we'll take advantage of that particular functionality in a second. All right, so I want to create a list of x values to go on the bottom of my chart, and I want to see all of those y values that are in my defect count, the 8, or the 24, and the 24, and those things. And I want to store them in 2 separate lists so I can dump them into matplotlib. So for those who haven't seen it, this is a list comprehension syntax. I'm not going to go into it, but it's very useful for doing analysis. I'm not going to talk about these. These are all just the things that we use for matplotlib. And it's going to take all of the x values that we just made and all of the y values that we made, and it's going to plot them. All right. And so we get this nice little chart. And a couple things that we can see right off the bat. Where are most of the things? Low end, right? There appear to be 2 little spikes. Do you guys remember what numbers those spikes were at? What were the most common values? 6 and 8. Right? When we looked at the data and I said, hey, I got this stuff kind of organized, there was a big number at the front. It was a 99, and sure enough, we see there's a little spike over there by the 99. Turns out maybe that's an outlier. Maybe not, right? Okay. So this visually shows us a lot of cool things. I want to figure out how do we get to some of these data points using code. We'll start off with using count, maximum, and minimum. What function do we use to count things in Python? Len, right? Stands for length. So if I have number of defects and I drop it into the len function, it will tell me that I have 204 data points. And you can essentially count just about anything in Python using len. Right? If I want to find the biggest value in a set or the smallest value in a set, what functions do I use? Max and min. All right, so let's do that. Let's take number of defects, we'll drop it into max, drop it into min, and we get that big value of 99, and our smallest value happened to be a 2. Sweet. All right. A lot of statistics is basically telling you stuff about your data. How many pieces of data do I have? What is the highest thing? What's the smallest thing? One of the things that we often talk about, like what's the average grade in a class, or what's the average weight of people in doing this thing, right? What's the average of age of folks in a particular group? Python has tools to look at that, and when statisticians look at that kind of information, they typically point to 3 main things: mean, median, and mode. Mean is also often referred to as average, and it's probably the one you're most commonly associated with. So I'm going to walk you through how we can calculate means, medians, and modes using my lousy code. All right. So here we'll start off with calculating a mean. If I drop a series of values into this particular function, it will try and figure out A, what is all of the a values added together, and then it will divide it by how many values do we have. Okay, so do that. And so let's just use a really simple set of values, these 4 things. The average should be like 2.5, if my math is right. And if I do this one, the average should be 3, right? Pretty straightforward. Anyone want to take a guess what the average is for our bigger data set? Any thoughts? What you got? Wow! That's amazing. Well done. All right. All right. Now, I'll show you in a little bit some other libraries that walk you through doing means, and we'll talk about some of the benefits of using those. All right. But now, I basically have an idea of kind of where is the average number, and it's somewhere in here between 9 and 10. Okay. Now, let's go look at medians. So median is a little interesting. The point of medians is to find the centermost value. If I've got 11 things, it'll find whatever's at position 6. If I've got 5 things, it'll find whatever's at position 3. Right? It doesn't really care if it's big, little, tiny, whatever. It just says, you've got this number of things, let me find whatever's stored in the center. All right. But there's a caveat. If I have an odd number of things, like 1, 3, and 5, the 3 is clearly in the middle. But if I have 1, 3, 5, and 7, what's in the middle? And how we typically solve this is we take an average of whatever the 2 things are in the center. And so my code will do that. The nuance here is before you find whatever's in the middle, you need to sort them. So we're going to sort all the values. We'll calculate how many values we have. We'll figure out what is the midpoint. And then we will return it. If we find out that there are an even number of values, we're going to do this thing where we average. We find out there's an odd number of values, we just give you the center point. All right. So I'm not going to walk you through the code in too much detail. You can take time to look at that if you want. But let's just see if it works. Sure enough, it gives me a 2. This one, remember, we have to sort first. So it's going to move the 42 to the end. And it'll find whatever's between the 5 and 6, which is a 5.5. All right. And I know this guy's already done the math in his head, right? He knows what the median number of defects, it's an 8. Okay. So we can take an average, which you're used to. We can take the median, find the middlemost point. Mode finds whatever shows up most frequently. All right. For this library, I'm also going to use counter to help us with this. We're going to count all of the values. We will find whatever value shows up most frequently, how many times it shows up. And then we will go in using another list comprehension. And if you're not familiar with these, I highly recommend you go figure them out because they're really awesome. We will go and say, all right, the maximum number of things was 24 things showed up. Let's go see how many items showed up 24 times. And this list comprehension will give me every value that had 24 entries in my count. So let's go take a look. Here, the number 4 is going to show up 3 times, so it will show up most frequently. So we should get back a 4. Notice, just a nuance here, with mode, I'm choosing to return a list of items. Because sometimes certain things, more than one thing may show up most frequently, like this list. 1 shows up 3 times, 5 shows up 3 times, so I want to get both of those back. So it's going to return a list with both of the things that showed up most frequently, the 1 and the 5. Just a nuance about that, right? We talk about kind of the average. Most of the time in our heads, we tend to think of there is only a single average. When you start talking mode, you can have bimodal or trimodal data sets where spikes of things occur. There's a book that I kind of like for folks who are new to statistics. It's Head First Statistics, and they talk about this ages for this group of folks in this class. And it's a class for adults and children to do like swimming together or something. I don't know. And when you look at the ages, the average ages, you have these very young children and you have these older adults. And so your average age is very different, and it's split. All right? So that's a thing that you'll see in many cases with mode. All right, so let's go look at the most frequent values in number of defects. It was 8 and 6, just like we saw earlier. All right, so a couple of nuances of when we might use these and some of the benefits of using them. I've got a little table here. Mean, you do this sum of the values, and you count how many values you have. You do the math. This is most commonly used when your data kind of has symmetry to it, and it has a single trend, one single spike. The median is often used with data that might be skewed a little bit to one side or the other and might have some outliers. It's kind of a way of dealing with the fact that your outliers will throw off some of your results. And then mode, it's different from some of the others because you can actually use mode with things that are called categorical data, and you'll hear that in statistics. What categorical data means is it doesn't have a number value. Like if I had a list of data and the data just simply said male, female, or the data said, you know, part A, part B, part A, part A, part B, part B. Those are all categories, right? And so modes can show us what is the most frequent part that showed up, what is the most frequent examples of things, and you don't have to have a number for them. So categorical data can be done with modes, and it's also good for things, as we mentioned, that have more than one trend. All right. We did a fancy histogram graph, but sometimes just having a quick frequency table can be really useful. And so a frequency table would be something like this, where it shows, hey, the value 9 showed up 3 times, the value 6 showed up twice. It's much like that counter example we looked at. If we look at our defect counts, the frequency table is not specific to mode. It is the counts of all your values. Mode is highlighting the things that show up most frequently. The frequency table shows up the values of all of them. Notice, where did it go? In my frequency table, it showed up that 8 appeared only once, where mode is going to show me the things that appeared most frequently. Mode would give me the value 9 showed up 3 times, or would give me the value 8 and 6 showed up 24 times. Does that help? Good. All right. So what I'd like you guys to do, and I'm going to shrink this down, give you guys a few moments to kind of start to wrap your head around some of these things. I'd like for you to calculate, and you can use my functions if you'd like. They're good enough for government work here. And go through this. Calculate the mean, the mode, the median, do a count on these things, and go through the exercises. And we'll give you guys a few minutes to do this. I want to caveat this for just a moment, though. Some people may not finish all of the exercises in the time allotted. That's totally fine. Go home, reread the material, do the exercises again, finish the exercises you didn't finish. That's all good. Just a little backstory here, right? And I'll show you my list of books that I've read. I've read these statistics books of various sorts over and over again. And even in the course of preparing this particular set of material, last night in my hotel putting final touches on, I was still picking up nuances that I had not seen before and still learning new facts and details that had kind of escaped me. So there's a lot to cover as we get further on in this conversation. So don't panic if you're like, oh man, I didn't get all of it, I didn't capture it. Yeah, I still go back and reread some of these books and catch nuances. So, all right, we'll give you guys probably about 10 minutes or so, and we'll wander around and answer questions.
Yeah, I'm fairly new to Jupyter, so this is what I did for the Jupyter lab.
All right. The little microphone appears to be back. All right. I'm not going to do the entire exercise. I'm just going to highlight one or two things. So mean. Let's see. Grab some of these guys. And say values. Right. And this was a nuance that I think Jeff had mentioned. Values, right? If you have two commands in a single cell, both of the commands will run, but only the last command will display to the screen. So if you wanted to have both of these display, you have two options. You could either put each of them, mean and median, in two separate cells. That works fine. That works fine. Or you can do some of that extra typing, and you can put the word print in here for the first one, and it will print, and you can put median values. So it will print the first one, and then it will execute the second one. Notice we get a slightly different output. Print actually displays to the screen. Median values actually executes and is released as an output. But that's a nuance. All right. So let's see. Let's talk about measures of dispersion. How widely spread is your data? Is your data really tightly clustered, or is your data just all over the map? You will sometimes hear in statistical books about things like measures of variability, how much does the data vary, or measures of spread. They all essentially mean the same thing. A fast and dirty measure of spread is simply, let's look at the minimum, look at the max, and see how far apart they are, right? And so that's what this does. My data range function just says, what's the max, what's the min, and divide or subtract one from the other. And so with my little data set, 5, 3, 4, 2, and 1, the smallest thing was a 1, the biggest thing was a 5, and the spread is 4 points. Notice with my batch defects, the smallest value was a 2, the biggest was a 99, so my spread is 97. That's a lot. Remember that 99 is potentially even an outlier or something. So here I can see that my data is really far away from the median and the mode and the mean, right? So this may be a flag, or maybe something of interest. It will depend on your data. All right. A couple of the downsides, though, of using simple spread are the fact that they are very susceptible to outliers. Here I have two data sets that are almost identical, except for the last two values, the 8 and the 99. You would probably say these data sets are pretty much the same. And so when I have this one thing with this minor outlier, man, it throws everything completely out of whack. And it makes it really hard for me to realize or to know that essentially these data sets are basically the same. All right. So how do we get past that? That's where things called quantiles and interquartile ranges come into play. Let me zoom in on this just a smidge. All right. So you're going to hear some of these words. These are the words that really bothered me. I never knew what they meant for a long time. A quantile it's a cut point or a dividing point, right, in a sequence of values. And those cut points will break those values up into what we call contiguous intervals, or intervals that butt right up against each other. So they have a nice continuous flow. And those cut points are defined, essentially, so that they break up all of your values into equal probabilities. The stuff in this lower quantile has as much probability as appearing as the stuff in the middle, et cetera, et cetera. Quartiles are values that cut your data into quarters. They are essentially a quantile that breaks things up into every 25%. An interquartile range is a range between your lower quartile and your upper quartile. Normally, that's between 25% and 75%, although you might see them with different values. All right, so let's put this into practice and see what we got. All right, quantiles. So again, these are kind of these cut points. If I have 6 values and I've got a cut point in the middle, it breaks my values into 2 sections. That middle, in our case, would be the median. If I have a lot more values, I have a value 1 and 62, 63 and 64, 65 and 70. This breaks up my range of values into 10 quantiles. And potentially, if I want to kind of weed out some of those outliers, I could say, I really only care about all the things that fit between this lower quantile and this upper quantile. And so I kind of filter out whatever's on each end. And that gets rid of the 1. It gets rid of the 99. All right. So let's make a function that helps us calculate where a given quantile falls. So I make this very simple function, give it a handful of values, and tell it where you'd like your quantile to break. And it will then figure out in a list of values or sequence of values, where does that fall? What is the index of that point? And then allows you to get back a value from your list or your sequence. Again, this is not robust code. Do not ever qualify this or use this in production. But it's good enough for what we need to do here. All right. So I've got a list of like school grades. There's 10 values. And I say, hey, I want to find the break point, whatever's in the middle. Essentially trying to find almost a median. It sorts everything first. 55 ends up at the bottom, 96 at the top, and then it roots through. I'm going to caveat this, right? This code was not sophisticated enough to realize that if I have even numbers, I should take an average between the two. This is, again, just to give you guys a demo. If I had an odd number of values, 11 in this case, we can use that as well, but again, it's not going to be very precise. All right. What if I want to find those quartiles, the 25% value and the 75% value? I take these grades and I say, hey, look for whatever grade is closest to 25% of this sequence of values, and give me whatever is closest to 75%. And so 67 is kind of the lower bound of the lower 25% of my students, and 91 is kind of the upper bound of the upper 25% of my students. Now, all right. If I want to kind of see where my defects break out using a variety of percentiles, like the lower 10%, the lower quarter, the upper quarter, 90, 95, and 99, I can do that. And so the value of 4 is right at the boundary of the lower 10%. The value of 6 is at the boundary of the lower 25%. We notice that value of 99 is way above the 95th percentile. Okay? So if I were to say I only want to see stuff between the 25 and 75, I filter out all the lower end stuff, I filter out all the high end stuff, and this is a great way to kind of get a sense of what the middle of the pack looks like. So let's do that. We'll apply what we just created to look at some interquartile ranges. Commonly you'll see like 10 and 90, 20 and 80. Depends on what you need. In our case, we'll have a lower quartile boundary, an upper quartile boundary. And I tell it, hey, here's the values we're going to give. It's going to use my function quantile from a minute ago and say 75 is my default value, 25 is my not default, or my lower boundary. And let's see how this works. It says, Chalmer, if you give me these 10 values, 3 is roughly around 25% of the way up, and 8 is roughly 75% of the way up. All right. If I want to then do that math and say how big a spread is this, I just subtract one of them from the other, and we see that 8 minus 3 is 5. So let's do that with my batch of defects. And it says, hey, Chalmer, if I'm only looking at 25% and 75%, your range of values was only 6. It's only a spread of 6. Right? Now that function I created seems a little weak because it's built in. It hardwired in 75 and 25. So let's build upon our function a little bit, and let's give ourselves the option now of adding an upper bound of our own choosing and a lower bound of our own choosing. Okay. And so I'm going to look at my number of defects, but this time I want to look at everything from 10% all the way up to 90%, and I'm going to see how big a spread that is. And here that spread is a little bit bigger, a little bit wider. All right. So what are the downsides of using an interquartile range? It seems like, hey, I can kind of filter out those outliers. That's good. Interquartile ranges, they only tell you really the difference between a high value and a low value. How far apart are they? They don't really tell you how closely they are knit to things. It doesn't tell you how frequently those high values occur or how frequently the low values occur versus how frequently the stuff in the middle occurs. So we would theoretically want a method to more accurately measure variability, and we'll look at that in a minute. So we'll give you guys a break. If people need to walk around, stretch, whatever, you can do that as well. Spend a couple minutes here, say 5. Walk through calculating a simple spread, calculating some quantiles, and then calculate an interquantile range for these numbers. And of course, I'll answer questions. One nuance for this second one, you guys should pay attention here. We're going to use the range function to create a sequence of values from 200 all the way up to, but not including 300. So if you've never used the range object to create a sequence of numbers for you, we have that here. This is how you would do it. All right. And we'll cut you loose. When you're done, put up your little green stickies. If your green sticky is still up, take it down. Awesome. All right, folks. So if I want to bang out an interquartile range for all of these guys, I can say range 200 to 300 with a step of 5. All right. For those who are not familiar with the range function, the second value that you put, range will go all the way up to it, but it will not include that value. And this third number you can give the range function tells you what step to take. And let's see, to calculate my interquartile range, I want a 0.25 and a 0.75, but those are the defaults. So heck with it. Let's delete that, and we should get back a 50. And that sounds about right, because there's about 100 difference between the two. All right. So let's talk about something way more fun. Let's talk about variances and standard deviation. All right. So there's a couple of different techniques that we can use to evaluate the spread of data that's a bit more effective than simple interquartile ranges or simple spreads. Interquartile ranges is good for fast and dirty. It's very nice. But variance and standard deviation are one of the workhorses for statistical evaluation. One thing that you may be tempted to say is, well, if I want to get figure out how much things vary, I could take the average of, I could take the average and I could subtract that from each of my values, and I can get this average difference from the mean. And that may look like it'll work, but what ends up happening is all of the things that are above your mean and all the things that are below your mean cancel out. I'll let you guys read the details. We're just going to skip right by that. Let's talk more about variances. Okay. With a variance, we do something very similar. We have an average, and then we subtract the first value from the average, the second value from the average, the third value from the average, and we square that to get some sequence of numbers. The benefit of squaring, which doesn't happen in that previous thing that I skimmed over, is that these all end up being positive numbers now. They can't cancel each other out because some are positive and some are negative. And so in this case, I have these three numbers, 1, 2, and 9. The average was a 4. I calculate what's called the variance, and I get this number, 38. And that gives me some sense of how much, or it gives me a total of 38, and then I divide it by 3. Sorry. Math is hard. I divide by 3, and I get a 12.6. So it gives me some sense of what the variance is. And you may look in your head and you go, I don't even understand what variance means, because how did I get a 12.6 to tell me how much stuff spreads when my numbers don't even get up to 12? I have a 1, 2, and a 9, and you're going to tell me, quote unquote, the variance is this 12.6 thing. And so some of you are sitting there and you have this quizzical look on your face, and that's the same quizzical look that everybody has, which is why we go one step further and we use a thing called standard deviation. Before I talk about standard deviation, the nuance here, though, that you can get is if I were to change these numbers and spread them out a little further potentially, my variance may get bigger, my variance gets smaller. So if I have two sets of data and one variance is large, one variance is small, the one with a larger variance is spread out more. The one with the smaller variance is spread out less. So the number itself may not jump out at you and you go, that means something. But numbers or variances from separate data sets can give you a sense of one spreads out more than the other. But again, variance is kind of this nuanced thing, like people are like, I don't even know what that means. So we'll do a function, we'll look at this happening and working, and then we'll move on to standard deviations. All right. So I calculate this by using the total number of values. I have a function that calculates the difference between the means. I square them. I will let you guys do this. Again, this is not production code. This is Chalmer sitting in a hotel room. But let's try and detect or determine what the variance is for our number of defects. And we're going to get some bizarre number. Our variance is 80. And again, that means nothing to me, right? I don't have a sense for what that means. because no one gets a sense, some folks thought this through and they're like, is there maybe a better way? And standard deviation is a potentially better way, and I'll show you some examples of why. To get the standard deviation, you calculate the variance, and then all you do is you take the square root of it. It's pretty straightforward. So I calculate the variance, same way. I get 38, divide that by the total number of items. I get a 12.6, and I take the square root of that, and I get 3.55. And again, you kind of may be saying in your head, I don't understand what that means. The nuance is that as your standard deviation gets bigger, it means it spreads more. As it gets smaller, it spreads less. But, and we'll see some graphs related to this later, that standard deviation fits very nicely on your graphs in a way that helps you to get a good sense of how things play out. All right. When we use data sets and we calculate a standard deviation, one thing that they have found is that on a typical kind of bell-shaped distribution, a normal distribution, and a lot of data tends to fall into that category, if I calculate the standard deviation, kind of how wide is the spread away from the mean, 65% of all of my values are going to be within one standard deviation of my mean. 95% of all my values are going to be within 2 standard deviations, and 99% will be within 3 standard deviations. So let me shrink this down just a smidge so we can see this all on the screen there. All right. So I have an average, I have a mean in the middle. I've got some sort of bell-shape-ish curve. And if I can calculate my standard deviation right here, standard deviation above the mean and 1 standard deviation below the mean, everything in this gap is going to be 65% of all of my numbers. Will fall right there in that middle zone. Boop. If I stretch out 2 standard deviations above the mean and 2 standard deviations below the mean, 95% of every one of my numbers is going to fit nicely in that little grouping. And if I calculate out 3 standard deviations, 99% of the stuff. So you say, well, how do I use this? What does this mean? Well, much like we use the interquartile range to say, let's drop all the values that are 25% or below, all the values that are 75% or below or above. We can use standard deviations to say, I only want to see the 99% of the values that are closest to the mean. And any of these little outliers that are way out there in the far corners, let's ditch those. Or I really want to get kind of a little closer, and I want to see 95% of my values that are closest to the mean. And so standard deviations can help us grab those when we're using something like a normal distribution. This may not apply with other distributions, but it works quite nicely with normal distributions, these bell-shaped curves. All right. Let's see. This first picture, kind of spiky. The data is fairly closely clustered on the average. This next picture, a little less spiky. It's a little wider. And in this case, because the graph is a little less spiky, my standard deviation happens to be bigger. And so remember, I mentioned that like if you're looking at 2 different data sets and a standard deviation is bigger, it means that data set spreads out more. And so because this spreads out more, my standard deviation is bigger. But the same rule applies. Even though this spreads out more, if I want to get 99% of all my numbers and drop off the 1% outliers, I measure out 3 standard deviations, and boom, I've got the 99% that I care about. Okay. All right. So I've got a fairly straightforward, and let me make sure I ran the variance formula earlier. Let's see, diff mean. So I got a fairly straightforward standard deviation calculation here. It uses my variance function that I created earlier, does the math. I have a fairly narrow data set. All the stuff is pretty close together. The mean is 5. We have another one that's a little bit broader. It goes from 1 to 9. But the mean is also still 5. And so let's look at how these 2 things calculate out. The mean is 5. My standard deviation was 1.4. This is a little bit broader data set. Still has the same average, but my standard deviation is a bit bigger. So now I can immediately go, this one is a flatter bell than this one potentially, right? All things being equal. Okay.
How do you interpret that?
How do you interpret that?
In other
What does it mean? All right. The nuance here, essentially, is that when you're looking at your data and you want to kind of know, I have an average, how much does stuff spread out on one side or the other or both? The standard deviation is going to point you in the right direction to say, this is really close to the mean, or these are very far from the mean. And so in this case, my numbers start at 3, they go to 7. They're all really tightly clustered around the mean. This one starts at 1, it goes up to 9. They're spread further out. I can immediately tell that there's a bigger spread between two data sets. Just looking at one data set and knowing that, okay, the standard deviation is 1.4 may not tell me a lot about that one data set. But being able to compare them is really useful. Another thing, as that number gets smaller and smaller, it means your spike is a little spikier, right? Things are narrower, things are closer. And a key role for the standard deviation, again, is kind of helping you figure out, how do I get rid of some of those outliers? How do I look at my data set and say, I only want to see the stuff that's from like 1% all the way up to 99% and not look at the things outside of it? Or where should my cut points be to look at just the 95%? Where should my cut points be to look at just 65% of the data? And so standard deviation can help you with that. All right. Did that help?
Yes.
Good. Let's talk about how real Pythonistas calculate standard deviations and variances and those types of things using real Python libraries instead of my hotel code. Okay. We're going to look quickly at 4 different libraries. And I will highlight a gotcha that may strike if you do not pay attention and if you don't kind of dive into the nuts and bolts. So the 4 libraries we're going to look at, there is a statistics library. This is brand new in Python as of version 3.4. It incorporates a sequence of statistical functions, and it comes with Python. So if you download Python all by itself, you've got it. You don't need to get any third-party libraries, which is quite nice. We'll look at NumPy. NumPy allows you to build these array objects and allows you to do very sophisticated calculations on these types of objects that are very fast. Has techniques and tools for integrating C and C++ libraries and Fortran code, again, to get close to the bare metal and make your code more efficient and more faster. It has techniques to be able to broadcast calculations and evaluations against large arrays of data without having to write for loops and stuff. And it's useful for like linear algebra and those types of things. SciPy library has a collection of mathematical algorithms. It's got some convenience functions that are built on top of NumPy because it uses NumPy under the hood. Adds a lot of power to your Python sessions. And then we'll look at Pandas, which is a common data science library. It does data analysis and those types of things. All right. So we'll start off by importing each of these. For some of these libraries, it's fairly common to import them with an alias, like import NumPy as NP. It makes it easier to type some of the commands you might want to use later. All right. I'm going to start off by creating a simple NumPy array. And we're going to use my defects batch file. Okay. One of the things that I often mention to students who are using a new tool, a new library, and they're making new data types, I often recommend to them that they do a couple of things. When you make a new object, I often tell them, go find out what the heck this thing is that you just made. And so I say, hey, what is defects? And it says, hey, Chalmer, defects is a NumPy array. And if I've never used a NumPy array, I maybe need to figure out what that means. If it spat out and said, hey, Chalmer, you just made a list, I'm pretty familiar with lists. Because this is a NumPy array, and I don't really know a lot about what NumPy arrays, right? I might want to try and get a sense of what types of functions or methods are available to me. So we're going to use a technique called tab completion. And this is really useful in Jupyter Notebooks. I type out defects, I put a dot, and I hit tab. And it brings up this list of all the types of methods and functions that are available to me. All right. There we go. Nothing like moving your laptop in the middle of a talk. Okay. Notice this is in alphabetical order, right? So it says things like all and any and da-da-da-da-da. And now we go into the B's and the C's and the D's. And this is a huge list of things that you, if you are mathematically and statistically minded, can do with a NumPy array. You can't do these with lists, etc. We are not going to go into the depths of this. I'm just going to kind of scroll through, get a sense there's a lot of things here. Notice they do have a method in here called STD, short for standard deviation. They have a method called var, which is standard for short for variance. All right. I'm going to start off simple, and I'm going to say, hey, let's use the mean function. And so we'll calculate mean. And sure enough, the average is 9.96, as this fine gentleman mentioned earlier. Right. I will caveat, there is no median function associated with a NumPy array. The NumPy library has a median function, and you can drop your array into the median function, but there is no median function that hangs off of your array, which I found very interesting as I was researching this. So we say, give me the median, and sure enough, it spits out an 8, and that's quite nice. If I want to look up the variance and the standard deviation without using Chalmer's crappy code, we get an 80.8 and we get an 8.9. Awesome. Let's turn to SciPy. I'm going to run all 4 of those, mean, median, var, and standard deviation. We get 9.96, we get an 8.0, 80.8, and 8.9. Looks good. One thing you should know, as I mentioned, SciPy kind of rides right on top of NumPy. So if I go in here and I say, I like this NumPy mean method, but I'm not real sure how it works. I'd like to know more about it. You can ask this question mark, and you put the question mark in there, and it'll give you the help file for it. So look at that. And now we have access to all of the arguments that I can give it. I give it my array, and if I want to do certain things, I can have it change its behavior. I don't know what any of these mean, right? Axis, D-type, what is all of that? Well, I can scroll through, and it will define for me, oh, here's what axis means, and here's what D-type means. And so I can figure some of those things out. Tells me what it gives me back. It says, I'm going to give you back this, that, or the other, and you can kind of get some sense of what's going on. Might give you some notes as to other things you might want to look at to see if other types of calculations might be useful to you. That's cool. Happens to be really nice and give you some sample code. If you tried to get it to work and it failed, maybe you look at the sample code and it helps you out that way. All right. Gives you some caveats. In certain cases, this might be slightly inaccurate. Buyer beware. Okay. It tells you where it pulled it from, and it said, hey, you know what? We got this out of the NumPy library, and it's from this thing called fromnumeric.py, which is awesome. If I were to do this same thing with scipy.mean, we see I can call scipy.mean, but interestingly enough, all the documentation is exactly the same, and when I get down to the bottom, sure enough, it actually just calls NumPy under the hood, so like I said, your mileage may vary. Okay, the statistics library. Statistics library has mean, median, variance, and standard deviation. Notice the spelling is different. Right? They actually call it variance instead of var. They call it stdev instead of std. All right. And if I run that, what's wrong? My numbers are different. In particular, which 2 numbers are different? The variance and the standard deviation here are not the same as the ones we saw before. So let's go take a look. 81.2 and 90.0. Oh, there's a lot of stuff here. And we had 80.8 and 8.9. So they're different. All right. Why? Anyone know why? Yes. He mentions there's a difference between population variance or population standard deviation and sample variance or sample standard deviation. All right, so now that our heads explode, let's go take a look at what that means. When you calculate what's called a population standard deviation, you are looking at the amount of dispersion for an entire population. And we use a particular formula for that. This formula, we take the difference from the mean for every one of our values, take the square, we divide by n, and we then take the square root. So n is this denominator. And in this case, for population standard deviation, the n is a larger denominator than the next example we'll look at. All right? And for your convenience in later reading, I spell out what each of the symbols is and why they're there. Let's go look at a sample standard deviation. A sample standard deviation is just a sample that estimates what your deviation for a bigger population should be if we take a random sample out of that bigger population. And it uses a slightly different value as the denominator, n minus 1. Because n minus 1 is smaller than n, the size of this standard deviation tends to be a little bigger than for populations. All right. So when do we use population versus sample? We tend to use the population when we know the entire population. We have all of the data in our hands. We use the sample version if we are looking at a subset of a much bigger group of folks. So if I'm a teacher and I have 25 students and I have all 25 grades, I can use the population because I know everybody's grades. If I am looking potentially at my students' grades as some sort of a sample of the grades across the school or across the school district, I don't have all the grades for the larger population. I just have my sample, so I have to use the sample standard deviation. All right. Another example, if I'm a researcher and I'm looking at the relationship between women, exercise, and blood pressure, right? I might use a sample standard deviation because I only have a subset of folks that I polled or surveyed or researched on. I don't have all the folks in the world, right? Okay. So that's why we have this difference, because that silly denominator at the bottom is off by a smidge because we're either looking at a sample or looking at a population. All right. The numbers are typically going to be very, very close together. If you're doing comparisons one to another, but you use the same formula, your comparisons will give you an order of magnitude difference. All right. If you were in a competition, like a data science competition, and you need to have the right answer, you may want to choose the right function. All right. So let's go look at one last example. This is the pandas library, and it has mean, median, var, standard deviation. Notice they went back to this kind of spelling of var and std. Let's run these guys. It uses that same version of variance and standard deviation that the statistics library did. Okay. All right, so just a nuance. Be aware that it happens.
What does the series do?
Oh, sweet. For those who don't know, pandas in this library allows you to create a set of data, and I take a list, I drop it into this series function, and I ask Python, what do I get back? PD. I say, hey, you have a series. And you go, okay, so what is a series? A series, essentially, is a column in a data set. You can imagine a series being like a column in an Excel spreadsheet. So it takes this list of things and throws it into a column. You say, well, what does that look like in real world? Defects PD, print it out. And so it says, hey, row 0 had a 99 in it, row 1 had a 52, row 2 had a 42. And it's got all 204 pieces of data. This is not a pandas class, but with a pandas series, you've got all sorts of capabilities. Like you can do aggregations, and you can do groupings, and you can calculate means and medians, and all sorts of other things. There's about 224 different types of things you can do to a pandas series to help you do your data analysis. You can break it up by quantiles. They have a whole library for helping you with, or a whole module for helping you with quantiles and stuff. It's a lot of cool things. All right. Did that help? Okay. 2 more questions. Go.
How easy is it for you to shoot yourself in the foot because your data set isn't matching the kind of data set that the standard deviation will be 65, 95, 99?
So what if your data set, for example, doesn't fall into kind of a nice normal bell-shaped curve? All right. So that's a really good question that I do not know the answer to, of how well your data needs to fit in the normal distribution for that to work well. I don't know if Alan has any insight into that. The question essentially is, yeah, there's lots of curves. But the question was, when you have a data set, if it's not necessarily a nice bell curve, and I try and do a standard deviation, how easy is it to basically shoot myself in the foot, right? If my data doesn't fit a normal curve, is my standard deviation just going to give me really wonky answers?
Definitely with crazy outliers, like very large values will drag the variance and the standard deviation up really high.
Mm-hmm.
And then the heuristics that you outlined, where 65% fall within the standard deviation and so on, those rules won't apply.
Sure.
How often is it like, will it be obvious if I look at the curve whether it's not going to do, or it can be slightly bit off?
So that is one of those nuances that regularly using these tools and reading about it, again, this is a 3-hour class, right? Diving into this. One of the great things that you'll see when you start looking at research papers where people are using statistics to prove a point is they use statistics incorrectly. And the point they're trying to prove is not what the data really shows, right? And it's not because necessarily that they're being malicious, just because they're trying to apply a thing, round peg into a square hole kind of a thing, and that just doesn't work. So it takes time. It takes effort to dive into this, research it, figure it out. I will show you some of the things that are available to us in some of the tools like SciPy, and just, it is mind-blowing the number of options that we have available to us. And so that would play into kind of your question. Yeah. You had a question too?
For NumPy, SciPy, and Pandas, you already mentioned this, but what kind of standard deviation do they use? Do they use the population, or do they use the
All right. So if a standard deviation is larger, it tends to be sample. If it is smaller, it uses population. So let's go back and look. Right. Well, if I dump the same data set, and let me get rid of this guy, clear output. If I have the exact same data set, which I do, I'm using num defects, and I drop it into SciPy, I get a slightly smaller value than I got when I put it into the statistics library. So a smaller value means a library is using population standard deviation. A larger value means it's being sampled. But having said all of that, there are ways to tell the library to do the thing that you want. So let's take a quick look at that. All right. Okay, so SciPy dot. In the SciPy library for standard deviation, they have a thing called this delta degrees of freedom, and it identifies the divisor that you want to use. And so you can have n minus something, and then the normal is n minus 1, right? The default that they use is 0. So if I needed SciPy to do the reverse of what it normally does, I can simply go into the function, and I can set this degrees of freedom to be 1 versus 0, which is the default. All right. So again, it's just a matter of, you need to know that it's there. You need to know it's kind of a problem that you have to kind of answer. All right, let's see what else we got. I think in the interest of time, holy cow, how did the day go by this quickly? We're going to skip the exercises. Here's a list of cool books. And I start from the lower end of the scale to the higher end of the scale. My first book I ever read on stats outside of high school was this cartoon guide. It was a low-pressure guide to statistics. It covers way more than we're going to cover in these 3 hours. The manga guide I got from my kid. He liked it. Head First Statistics by O'Reilly is a book that spells things out in a way that I find to be really, really useful. Naked Statistics is a little less about how one does it and the maths, and more about, oh my gosh, how do you not do it wrong? And he talks about a lot of good kind of case studies and examples of people using statistics and the pros and cons. He's very light on the math, more on the this is awesome statisticness. So this is a great read. Statistics in a Nutshell, that's fairly dense. It's a good reference book. I like it because it puts all the stuff in a small amount of space, but I found that had I read it before I read maybe Head First or even the manga guide, that might have been a little too intense for me. Think Stats, Think Python, and Think Bayes are great. And for those who don't know, that guy over there, he wrote them. And this one is a little wonky. And if you go to Amazon and you look at the cover of this, you're like, oh my gosh. But it is very compact, and it spells out a thing called Bayes' theorem. And it spells it out in a way that's kind of visual, and it was quite nice. All right. And for the record, Mr. Allen, who literally wrote the book, yesterday we're talking, he's like, hey, do you want a mentor in your class? And I'm like, yes. Okay, so he's judging me, by the way. All right, thanks. So let's move on to the next thing, and let's cover this. Let's go through this. We're going to shift gears. We're going to talk about probability now, the likelihood of something happening. We're going to figure out how we can calculate the probability of something happening. We will explore probabilities using what we call Venn diagrams. We'll explore probabilities using probability trees. And we will talk about the principles behind the law of total probability and behind Bayes' theorem. And we'll see a couple of examples of that. All right. I like the definition from Sarah in Statistics in a Nutshell. Probability tells us how often something is likely to occur if we repeat an experiment, right? So let's expand our understanding of probability with a couple of definitions. You'll hear references to a thing called trials or experiments or observations. A trial is some event where you don't yet know the outcome. Trials can be crazy easy. I'm going to flip a coin, I'm going to roll a dice, or it could be someone has a low birth weight. Will they graduate from college 22 years later? Right? Sample space is essentially all of the possible outcomes of a trial. So I have a 6-sided die, I roll it, all the possible outcomes are 1, 2, 3, 4, 5, and 6. Say I drop 4 coins in a bag. I've got a quarter, a dime, nickel, and a penny. If I draw one of those out, my sample space will be quarter, dime, nickel, and penny. An event is the actual outcome of a trial. Events could essentially be singles or could be groups of things. We will often designate an event with an E. So if I roll a die and my event is that I get a 1 on my die, E would be this set with 1 in it. If I want to specify that my event is that I get an even number, my E would be a 2, a 4, or a 6 when I roll that die. So you can have more than one thing in your event. Now, if I'm going to calculate a probability, this is pretty straightforward. I take how many elements are in my event, divide that by how many elements are in the sample space, and I get the probability. So the probability of rolling a 1 on a 6-sided die is 1 divided by 6. And that math turns out to be like 0.16 or something. So let's throw together a pretty straightforward function that will help us do this. For those who do not play D&D and those types of games, a D6 means that your die has 6 sides. A D8 means it has 8 sides. So let's make a real quick function that returns a 1 on a D6. And so I would calculate 1 divided by 6, and I get back, sure enough, 0.16. And that's crazy limited. You would never want to write multiple functions for every single case. So maybe we want to expand this a little bit, make our probability function better able to handle a large sample size or better able to handle an event. So I set my count to be 1, and I divide it by the sample size. All right. So if my event was I roll a 4 on a 6-sided die, the probability of a 4 showing up is this. The astute observer, though, goes, wait, Chalmer, we dumped in event, but we never actually used it. That's screwy. Let's go fix that. All right. If my event is composed of more than one thing, I want to determine if I get a 2, a 4, or a 6. We need to have a way to determine that. All right. So I'm going to make a small list. Let's say my event is I roll less than a 4. I roll 1, 2, or 3 on my die. I start off with saying, hey, let me check. Did Chalmer just give me a list or a tuple, or did he give me a single value? If he gave me a list, we'll count how many events are in it, 1, 2, 3, and we'll use that to do the math. If he gives me a single item, then we'll just call it 1. It's all good. All right, so one thing that we often do in Python is alias things, maybe give them shorter names. I do not want to type probability a lot, so I'm going to give that function a new name called p, so it'll make it easier to type stuff. So if I have a 6-sided die, I have 6 items in my sample space, and I'm looking for a 2, the probability is 0.16. On the other hand, if I'm curious, like what is the probability of getting a 4, 5, or a 6 out of a sample space with 6 items? That's 1/2. All right. If I'm looking for odd numbers on a 6-sided die, 1, 3, and 5. Again, I have a 50% chance of getting an odd number. Alrighty. Picking out how many items are in a 6-sided die is pretty straightforward. But when things start to get a little more complicated, that's where Venn diagrams come in. And you guys have probably all seen these. We use these to represent elements in your sample space using very simple pictures. So I'm going to show you a representation of rolling the odd numbers on a D10. All right. So I've got a D10. It is fairly common in Venn diagram land to put some sort of a rectangle, and that rectangle represents all the possible values that you could have. It is also fairly common to draw some sort of an oval or something, or a circle, to show the things that you really care about. And in this case, I only care about odd numbers, and I go ahead and I label those, 1, 3, 5, 7, and 9. I meticulously went ahead and said everything outside of that oval is all the other stuff. I do that for clarity, but most of the time we don't bother, right? It is presumed or assumed that everything in the rectangle is all the other stuff. If I need more than one oval to represent 2 kind of related events that I care about, I can put more than one oval. We'll see that in a bit. Make sure I didn't miss any of the things. Okay. I'm going to have you guys go through your little notebooks, etc. Sketch out a couple of simple Venn diagrams. You don't have to make them huge or anything. Wrap your head around this idea. So this first one, for example, we're going to have one thing that we care about out of a list of 20 items on a D20. And then what I'd like you to do is put together some Python code that calculates the probability of getting 1 on a D20. This next event is a little bigger. I'm looking at just the odd items on a D10. I've got an example. I want you to consider what would we put together to represent, I think it's all of the aces? Oh, picking a single ace out of a deck of 52 cards. All right. And so write some code to do that. You have to figure out what your event space looks like, or your event looks like and what your sample space looks like. So spend a few minutes, do that, and put your green stickies up when you get done. There's about 5 or 6. I think what we'll do is we'll give this about 7 minutes, and then we'll roll on. So I'm going to set a timer, 7 minutes. Got about 2 minutes left, and then we'll roll on. Finished. Make sure you get the little green stickies up. Although we're running out of time. Again, don't panic, right? None of us is walking out of this room a guru, except for that guy. Thing is, though, he walked into the room a guru, so he had a leg up on all of us. About 23 seconds. All right. So let's take a quick look at this. I'll look at the one that kind of raised the most questions. Numerous people asked about this. So P, say I have 52 cards in my sample space, and I have 4 items in my event. A number of people typed in 52, 4. Our code is not yet sophisticated enough to deal with that. Our code balks. What we need in our code at the moment is to put in a list of items, right? So, you know, an ace of clubs, a ace of hearts, an ace of spades. Typing is a horrible thing in front of people. And an ace of diamonds, right? And say, hey, it's about a 7% chance of getting an ace out of a 52-card deck, right? If I were to type in a 4, I get a much lower percentage. And the reason being, if we go back and look at the code said, if it's a list, tell me how many elements are in the list. If it's just a number, we're going to consider that to be a 1. So we've discovered kind of weakness in the code, like, hey, this doesn't quite play nice. Let's go fix that. All right. But the long story short of these problems here, and these are kind of one-dimensional style problems, is what's the size of my sample space and how many elements are in my event space? All right, so let's go look at our code. To do that, though, we kind of want to expand on a few other things, and then we'll get there. Let's talk about exclusive events and intersections. Most of what we looked at are just very simple Venn diagrams, little circle with a certain number of things in it. There are some cases, though, where, as I potentially try to create a Venn diagram, I might notice that, wait, I'm looking at maybe 2 different types of things and trying to lump them together in my event. For an example, say I had a D10 dice and want to know the probability of rolling an even. So I have 10 sides. Evens are 2, 4, 6, 8, and 10. That's 5. So that's 50% chance of getting an even. Chance of getting an odd is also 50%. So the chance of getting either an even or an odd is a guarantee. If I roll my dice, I will get either an even or an odd. And so I can very nicely add these 2 things together, and boom, I can calculate what are the odds of getting, or what is the probability of getting an even or an odd. So yes, I have my little odd circle, my little even circle, and there's a total of 10 things in it. My space has got 10 things, so it's all good. But what happens if I do something slightly different? What is my probability of getting something that is greater than a 5? when I roll that 10-sided dice. I have a 6, 7, 8, 9, or a 10. What is my probability of getting a number that is even 2, 4, 6, 8, or 10? My sample space is 1 through 10. Notice greater than 5 and even have these kind of overlapping spots where 6, 8, and 10 fall into both of those ovals. If my probability of getting greater than 5 is 50%, my probability of getting even is 50%, and I add those together, that answer is not right. It would say that I have a probability of getting, or I have a guaranteed probability of getting one of those two things, and we know that's not quite true. The correct answer of getting either greater than 5 or even is actually about 0.7. And I use the word about, and it's quite literally exact, right? I have 7 things in this kind of conjoined event. 1, 2, 3, 4, 5, 6, 7. My total sample space is 10, so 7 divided by 10 is 0.7. So what went wrong? Our original kind of let's add these two things together ignored, unfortunately, the fact that there's a little bit of overlap. So we have this very cool formula that allows us to account for overlap. I have the number of things in one event, the number of things in a second event, and if there's any overlap, I just subtract out how many things overlap so I don't double count. That ensures that I single count those. Divide that by the sample space, and I get the union, or the OR, of A and B. All right, so that's the generic formula. You notice I have this kind of U-shaped thing, and I've got this kind of upside-down U. The upside-down U means the intersection, where things overlap. Sometimes you'll see that referred to as a cap. So the number of things that are intersected between A and B. This U stands for union. It's kind of an OR. This is the number of things that are included in A or B. All right. So sure enough, we do the math. Greater than 5 is a 50% chance. There are 5 elements there. Odd is 5 elements. There's an overlap of 3. We do the math. We get 7 over 10. Okay. So let's start to explore this in practice. We'll use my little Python probability function. I put in anything that's greater than 5, anything that's even, and we subtract manually the things that we know overlap. And let's get an answer. And sure enough, we get 0.7. So what's the probability of drawing a single red card from a standard deck or drawing a king? Well, if I were to put that into my probability function, we would see very quickly that this would just suck, because I'd have to type out this big giant list with ace of diamonds, 2 of diamonds, 3 diamonds, 4 diamonds, etc. And nobody wants to type that. That's lame. So let's tweak our probability function to say my sample size is maybe 52 cards. My event could be a single element, or if I already know how big the event is, I can give it the event size. There are 26 red cards. I'll just say that the event size is 26. And then we add a little nuance in here. It says, hey, if event size is a list, count how many things are in the list. So we still have that functionality. If event size is an integer, just use that as my count. So we used a 4 before, right? All right, so let's run this. Boom. Probability of a red card or a king. There are 26 red cards in a standard deck. There are 4 kings in a standard deck. 2 of those kings are red. And boom. Let's go take a look at the answer. Before we get to the answer, though, sure enough, with 26 red cards out of 52, I have a 50% chance of getting a red card. With 4 kings out of a deck, I have a 0.7 chance of getting a king. But that little bit of overlap that we kind of have to suck out of there, that's 0.3. And I get an answer of, there we go. My chances of getting either a red card or a king are 0.53. It's a little bit above half, which is what we expect. All right. So what's the probability of drawing a red card or getting a face card? A king, a queen, or a jack? Well, how many king, queens, and jacks are there in a standard deck? How many jacks, queens, and kings? 12. All right, so I say, hey, I've got 12 here. There's 26 red cards. How many jacks, kings, and queens are red? 6. So I want to get rid of those because we do not want to double count them. And sure enough, it's a little bit higher because now we're looking at a few extra cards. All right. Now, you might say, but Chalmer, why do I want to do all this math and write all this code? Because if we think about it, all I need to know is how many reds are there, how many face cards are there, and take away how many duplicates, and I get 32. So I can actually just say my sample space, or my event space, is 32 cards are either red or they're kings, queens, and jacks. And so I don't necessarily have to do this if I can kind of do it in my head or do it manually. You just got to make sure that you get event A, event B, and you eliminate that duplicate, and boom, we get the same value. Awesome. So I'm going to, for those who don't know, PyCon has open spaces where people can gather with folks who do things that they like to do, and one of those open spaces is board gaming. All right, so here's a board gaming example. I have 3 games. I have Pandemic, I have Clank, and I have Carcassonne. And in my board gaming group, we have a number of folks who play Pandemic, a number of folks who play Carcassonne. The pronunciation of this French word is probably mangled by me, my apologies. And then we have Clank. Some of these folks happen to be players of Pandemic and Carcassonne. Some of them play Clank and Carcassonne. I have no duplicates or overlap between these 2 games. Now, everybody in this oval, this 12 and this 6, they're all part of a group. So there's actually 18 people in this group. This group has how many folks in the big circle? 16 plus 26. And then the Clank group has how many people in it? 12, right? When I was putting this example together in my head, I kept forgetting that these 6 folks were with these 6 folks, and so my math was always wrong. It was very annoying. That's why I pointed out. Pandemic folks, there's 18 of them. There are 12 clankers, but some of them play more than one game. All right. So what is the probability of finding a Pandemic player in my board gaming group who is also a Carcassonne player? Well, okay. Well, there's 18 of the Pandemicers. There's 26 Carcassonners. And then there's this nice little overlap of 6. We do the math. And about 86% of my board gamers play those 2 games. But again, if I don't want to type all this nonsense, as long as I do the math, 18 plus 26 minus 6 gives me a 34. We're all good. All right, there we go. And the math failed epically for some reason. Why did that fail? 18 plus 26 is 34. My event size is 36. There we go. That didn't work either. 18 is 26 minus 6. 18 plus 26 is what? 38. All right. This is awesome. I'm going to come back to this. This is great. All right. Based on the fact that the code may be horribly wrong in some incredibly awesome way, we're just going to skip those exercises and move on. Let's talk about conditionals. All right. During the next break, I'll take a look at that and try and figure out where my math and all of that stuff went awry. All right. Let's talk about conditionals, because this is going to lead to some fun stuff. one of the things that we really want to do when we start looking at probabilities is not just know when things kind of overlap, but we want to understand if one thing occurs, what is the probability that something else is going to occur? If I exhibit certain symptoms, cough, cough, hack, hack, sniffle, sniffle, what is the probability that I have a cold versus what is the probability of I have the flu? Or the probability that if I have a tummy ache and some cough, cough, that I might have food poisoning or something, right? So if you have one condition, what is the probability that you have something else? When we talk about probabilities, we often hear the word given. So if I know that a particular card is black, what is the probability? If I'm given that it is black, what is the probability that it is also a king? So I take a card out of a deck and I say it's black. You can tell me what the probability is that it happens to be a king. If I tell you I rolled a 10-sided die and the number came back and it was an even number, you can tell me the probability that it was a 10. Right? To help us do that, Venn diagrams sometimes break down a little bit. So a really useful feature, or a really useful thing that people will point to is this idea of a probability tree. So for example, I have a deck of cards. They have 52 cards total. Some of them are black, some of them are red. I know that 26 out of 52 are black, 26 out of 52 are red. If I tell you that a particular card is black, and I want to know what is the probability that it is a king, I know that out of all of my black cards, I have some that are kings and some that are not kings. There are 2 black kings, so there's 2 out of 26, right? And there are 24 out of 26 that are not kings. So there are 26 black items, and they kind of fall out in this way. Same thing with red kings. A couple of things. We often talk about kind of levels on the probability tree. So we have one level of my probability tree. We have a second level. With any set of branches here or a set of branches here, the math always has to add up so that the total probability on that set of branches is 1. Right. So for example, 2 out of 26 plus 24 out of 26 is 1. Right? 26 out of 52 plus 26 out of 52, you add that up, you get 1. You can have more than 2 branches. If you play roulette, you'll know that the squares on a roulette table are red, they are black, and there's 2 of them thrown in there for good measure that are green. So I could have a roulette table probability tree that might say black square, red square, green square. And I could have 3 branches. But nonetheless, the probabilities will all add up to be 1 on any individual level with a grouping of branches. Okay. To solve kind of across a single branch, to figure out what is the probability of getting to the end of a branch, you multiply the probabilities together. So if I want to say, I have a deck of cards, what is the probability that I will have a black king? I multiply 26 over 52 by 2 over 26, and that will tell me the probability that I'm holding one of the 2 black kings. So 26 over 52 times 2 over 26, and I have a roughly 3%, 4% chance of holding a black king. Right. Dear God. And so if 52 items, 26, multiply that by 26 and 2, I get this. Now, the rest of the branches play out the same way. Black and not a king, red and a king, red and not a king. The cool thing is, the probabilities at the end of each of the branches, the probabilities way out here, 3%, 3%, and then like 47 and 47, they all add up to be 1 as well. Right? So 46%, it's about 3 or 4%, another 46. And so when we add this up and we round it, because, you know, math being hard, the total probability for any single branch, when you add them all up, is a total of 1. And that makes sense, right? Okay. Now, When we draw probability trees, sometimes we throw out generic probability trees. That other one was kind of specific, king, not king. So you'll see this kind of nomenclature and syntax. If I care about all the elements in a group called B, anything that's not in that group, you'll often see it referred to as B prime. You might also see tilde B. It just means anything that's not B. So here, probability that I get a B, probability that I don't get B. This is B, this is not B. There's an A up there, not A and not A. Shrink this down a little bit. All right. So you'll see B prime, A prime. You'll also see this nomenclature here. That nomenclature is read in the following way. Probability of A given B. So what is the probability that I get an A given that I'm on the B branch is essentially what that means. Here, what is the probability to get an A if I'm on the not B branch or the B prime branch, right? So probability of A given B, given not B. Okay. And all that's spelled out in the text. All that leads us to a formula. If I want to know what is the probability that I get an A if I'm given a B, I can calculate for the union of A and B, or the intersection of A and B, and then divide that by B. If we pull out our algebra hats and we spin that around, the probability of A or B is the probability of A given B times B. Say, okay, what does all that mean? All right. If I want to know the probability across a branch, I simply multiply one of these by the other, and I'll get the probability for that branch. And this is going to be really useful to us in a second. But that's what this second formula means. To get to the end of the branch, I multiply the first level times the second level for the branch I care about. Now, a lot of times when we're given data, and we're going to try and make this really cool probability tree, we're not given all the data. That would be way too easy. So there's a couple of rules and helpful hints that allow us to build out a tree. Right? First rule is, or the first step we want to take is, try and define the level of the tree. In my black card, red card, king, not king, my definition of levels was, okay, I could get a black or a red, that's the first level. I could get a king or not king. I could get a king or not king, and I defined each of the branches. If I have facts, go ahead and fill them in. Put them down on the paper. I'll show you an example of that with a couple of pictures here in a sec. Once I've filled in all the facts I know, I can do a little bit of simple math and fill in a few of the facts I don't know. And then I can start to complete the branch groups, knowing that the probabilities always add up to 1. And I can use that cool formula to then figure out the last remaining probabilities. So let's see how this works. I go out with a bunch of my friends at work. Some of them eat burgers, some of them do not. Some eat dessert, some do not. Right? So maybe I want to figure out the probabilities associated with each of the branches, given that some of the folks in the company eat burgers or don't eat burgers, eat desserts, don't eat desserts. And I'm given 3 initial pieces of information. The people who eat burgers, 2 out of every 3 people eat burgers. Given that somebody is not a burger eater and they eat dessert, that happens in 1 out of 4 cases. And given somebody eats burgers and dessert, that happens 8 out of 15 cases. So let's start to fill this in. All right. Sure. Probability of eating a burger, given that they don't eat a burger, they eat dessert, and then probability across a branch, they eat burger and dessert. So as I start to fill this in, probability to eat a burger is 2/3. Probability that they didn't eat a burger but they ate dessert is 1/4. And the probability that they had a burger and dessert was 8/15. We know that this and this have to equal 1, so I can go ahead and start to fill this in. We know that this and this must equal 1, so I fill in the extra value. So we're moving along, making good progress. One thing that we're kind of missing is this guy out here. I know this, and I know this. And I know if I multiply this by this, I get that. So I can back out and figure out what this piece is if I know him and him. And this is just algebra. And when I say just algebra, some folks suffer with algebra in high school, etc. Don't panic. Just takes a little bit of practice. So I don't mean to say that algebra is crazy easy. All right. So my formula says, if I'm trying to figure out what is the probability of dessert and burger, if I know he ate a burger, and we know that he ate dessert, and we multiply that by the probability he ate a burger, this doesn't help me because I'm kind of missing something in the middle, right? I'm missing this guy. But I know 8/15, I know 2/3. We can do the algebra, flip this over and put them on the other side. And now when I multiply 8 times 3 and 15 times 2, and I round it all down, I end up getting a 4 out of 5. So I put 4 out of 5 up here. And if we kind of go back and double check our math, right? 2 times 4 is 8. 3 times 5 is 15. It worked out just the way we wanted. I know these two have to add up to 1, so I figure out what that is. Now I have all of the probabilities for every single branch. I know I can multiply this by that to get here, this by that to get here, and there. So now I can fill out the probabilities all the way across the branch. Okay, so this is useful. I now know that if somebody bought a burger and they didn't have a dessert, that happens 2 out of 15 of my friends. If somebody didn't buy a burger and they didn't get a dessert, 3 out of 12 of my friends are in that horrible, horrible group where they don't eat burgers and they don't eat desserts. All right. Okay. So let's do some math here with our script. Right. Here, I pulled all the values off that chart and I started to drop them in here. For branch 1, the probability of burger, not burger, was 2 out of 3. So 2 out of 3, 1 out of 3. Probability of dessert, not dessert, 4 out of 5, 1 out of 5, 1 out of 4, 3 out of 4. And if I add up all of these, it should turn out to be 1. And sure enough, it does. All right. So I have a reasonable level of confidence that my numbers came out the way we expected. All right. And this is going to set us up for a situation in a little bit where we can now move beyond this and we can answer some really interesting questions. All right. But for now, we'll take a little bit of a break. You guys kind of churn through this. What time does this thing end? I always forget. 4:20. 4 something. 4:40. Sweet. So we have a little bit of time. All right. So I'm going to turn it over to you folks. All right. I want you guys to take some of these pictures I produced for you. And this is going to mirror exactly what we just went through. You'll have some data. I want you to maybe put on a piece of paper or whatever, start to sketch this out, fill in the things that you know, start to fill in the things you don't, and then we'll go from there. Meanwhile, I'm going to go back and look at those two functions and figure out why I suck at math. Why did this fail? Sure.
Which is, I think that 52 is
Oh.
supposed to be a 46.
You are totally right. I could have swore I changed this because I saw it. And I could have swore I changed it. Yeah, that's it.
Can I get you a coffee or two?
I'm good. Thank you, sir. So everybody just fled the room. But they left their laptops, which means it's open season on unattended laptops. Pick the ones you want. And I'll come back with your question. Turn this off. wouldn't I wouldn't give for Microsoft Paint. All right. I want to go over something real quick. Turn on the thing. So, when I first started going down this road, I'm going to be perfectly honest. Lots of squiggly lines, lots of slashes, parentheses, crazy letters and numbers and things that mean absolutely nothing. Yeah, my mind exploded. It took doing this multiple times, over and over again, reading the topic in book A, rereading the same topic because I didn't understand it in book B, and then maybe sometimes rereading the same topic in book C and going, ah, I see what you did there, right? So, having said all of that, right? If you're trying to go through things and maybe you're drawing little probability trees and you're like, I don't know what number goes where, you're in good hands. Half the people in this room might have been in that very same thing and be willing to admit it. There's a bunch of other people in the room who are in the same boat, but we're not willing to admit it. Okay? In some of our examples thus far, right, we were given things. Here's a probability. Here is a probability of something happened given that I have a precursor, I have a condition. And then we have the probability that two things happen. This N is kind of like an intersection. It means and. Probably the guy had a dessert burger and a dessert. If we picture this and this, just those two for right now, single probability and a probability with this given symbol in the middle of it. And we scroll back up here. When I just have a probability, it goes first. When I have a given, it goes second. And so this given probability is up on this upper branch because it's telling me this probability of not getting an A only applies if I'm on the B branch. This probability of getting an A only applies if I'm on the not B branch. So this given statement helps you figure out where that particular value fits in any one of these four things. Right? And then the intersection of, hey, my friend ate a burger and he also, or she also ate a dessert, that intersection is at the end of our chain. If I know the probability ate a burger and I know the probability had a dessert, given that they had a burger, I can figure out that intersection. So, kind of mental model where these three things fit. Probability given that I'm on a particular branch, and then the intersection. And so hopefully that will help you start to flesh out where these things go. But again, I read book after book, looked at it multiple ways. Some authors are really horrible at explaining stuff. Some authors are really good. Some authors are genius. Right, so, yep.
Right there, that picture.
This picture.
Yeah, if you were to add up all the ones on the outside, the probability of burger, dessert, burger, not dessert, not burger, if you add all those up, do they equal 1?
Yes. The reason they would equal 1 is I have 4 possible options. There's no other options that my friends could have went down. They had a burger, didn't have one. They had dessert, they didn't. So I have 4 possible options. I have to fit into one of those 4 categories, and so the probability of getting any of them is going to be 1. All right. And here, when I solve for the probability of branch 1, branch 2, branch 3, and then I add up all 4 probabilities, sure enough, I get a 1. All right. So that's that. So let's wrap up this conversation here with this idea of the law of total probability and the law of Bayes' theorem, or Bayes' theorem. Okay. When we looked at those first probability trees, it was fairly easy to kind of hop from one step to the next. Hey, my friend had a burger, and 10% of my friends who ate burgers all ate desserts. That's great. But how do I reverse that question? If I'm talking to a friend, and my friend says to me, you know what, man, I went to the restaurant, I had this awesome dessert, it was crazy good, a little pecan tart. How do I figure out whether my friend ate a burger or didn't? How do I determine the probability of whether he ate a burger or didn't? Because if he says, or she says, I ate a dessert, I may know this value, like my friend is either on this branch or my friend is on this branch, but I don't want to pry. I would like to just kind of figure out the likelihood that they ate a burger. How do we get back to that? And that's where the law of total probability and Bayes' theorem come into play. So let's start with looking at the law of total probability. I'm going to apologize, right? There's lots of mathy, symbol-y things. So again, you're going to have to go back, review this, look at this, and kind of work through this. I'll blow this up a little bit so the font is slightly larger. Okay. So let us presume that I want to solve the following problem. Given that my friend said, yep, that dessert was tasty, how do I determine the probability they ate a burger? All right. We know that to solve for this, I need to know these two things. It's a formula that we had further up on the page. What is the probability they ate a burger and dessert divided by the probability that they ate a dessert? We may look at this and say, well, Chalmer already gave us a formula to kind of figure this out. If I want to know what that is, I just need to figure out what's the probability they ate a dessert given they had a burger times burger. That's exactly what we just did a few minutes ago. So okay, check. We can solve this. It's going to take a little math, but we can solve that. How do I figure out the probability they had a dessert? So that's something we're going to have to kind of figure out. Okay. If I take that little bit and replace whatever was in the numerator before, okay. If I replace this with this, so whoop, we're going to make a little bigger formula, but again, we kind of know all of these values here. We still don't know what dessert is quite yet. But we're getting there. We're filling this in with things that we can answer. I can look up the probability one of my friends normally eats burgers, and I can figure out what the probability is that they ate dessert if they had a burger. To figure this part out, I simply go out to the ends of each of the branches, and I look at the two branches that say dessert on them, and I say, what's the probability that somebody had a burger and had a dessert? What's the probability they didn't have a burger and had a dessert? And just add those two things together. And if I can add those two together, I can get the overall probability that one of my friends ate a dessert. Now, the magic becomes, substitute these, break them out a little bit, and we can solve for what the probability is they ate a dessert, and that is the law of total probability. All right. Let's take a quick look at this for a sec. So, knowing what we know, we can go through and do the same process and start to fill in the little blocks. We can start to multiply things out. We figure out the probabilities that I received spam or didn't receive spam, probabilities that there were keywords in the email or there wasn't keywords in the email, probability that something went all the way across a branch, and we figure out these numbers at the end. And with all of those things, I can go back too big, and I can start to fill in this part of this equation. I can figure out what the probability is the guy had a dessert. Okay. Once you know that, we can take that value, probability they had a dessert, replace it with all this nonsense. And now on this side of the equation, I can essentially go and look at my chart that I sketched out, and I can start to put a number in every single one of these spots. Hey, he had a burger. I know what how much a probability he had dessert. I know the probability they had burgers. These two guys are exactly the same. I know he didn't have a burger, and I know the probability they had dessert, etc. And so you can start to fill in all of those things. And if you can get those 6 values, I can now tell precisely the odds that my friend says they had a dessert, I know they had a burger or didn't. Right? So let's put this to the test. There's a lot of things going on there. Let's take a quick look. Given that a Spamish style keyword was found inside of a message, what is the probability that it is classified as not really being spam? Right? So given a keyword is present, what is the probability that it's not classified as spam? And you say, well, that seems kind of weird. If there are bad Spamish words in there, doesn't that automatically mean it's Spamish? Not necessarily. My friend says, hey, Chalmer, here's a great book on getting rich quickly, right? He's not spamming me. He's sharing something that he found. Whereas if I got an email from somebody, in a foreign country, hey, you want to get rich quick? Maybe that's spam. Okay. So you could have keywords, but the email may not necessarily be spam. All right. So I start off. I've got some values. We know from some of the research we've done that 7/10 of the email that comes in is going to be not spam. So I have a number to go with not spam. We know that if something is on the not spam branch, the probability that a Spamish keyword is there is 1/10. And if we know that, or we can also calculate that given something is spam and doesn't have any keywords, is 3 out of 100 things. So let's start to fill in that a little bit. All right. So we start to put numbers down. 7/10 of my email is not spam, 3/10 is spam. Something was classified as spam, but it didn't have any keywords. Maybe they're starting a new spam trend, right? Only 3 out of 10 things are spam, but don't have any keywords. This one is keyword, given the fact that it wasn't spam. Only 1/10 of the things that aren't spam have those keywords. So now we do all the things, right? Make sure each of these branches is equal to 1. These branches are equal to 1. These are equal to 1. We back this number out from there, and we start to fill this in. All right. And then we do the last bit of the math. We multiply this times that. So 3 times 9 gives me 27. 10 times 10 gives me 100. 7 times 1 gives me 7. 10 times 10 gives me 100. Fill in all these. All right. With every one of these values filled out like this, and as we practice and as we get used to it, it becomes fairly straightforward to get to this point. Apologize for the small font. I can essentially pluck values right off this chart and start going boom, 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 and I can fill in all 6 values. And now I can tell you, if I got an email that had some really cool Spamish keyword, what's the likelihood that it really isn't spam? All right. So let's blow this up a little bit. So on the top, I say, let's go find out if it isn't spam and there's a keyword present, what is that? So that is 1 out of 10. So I put my event size is 1, and I have 10 items. If it is not spam, that's a 7 out of 10. This is a 1 out of 10, 7 out of 10. And I fill in all 6 of these. And there we go. If there is a Spamish keyword in my email inbox, get rich quick, Cialis, Viagra, the odds that it is not spam in this made-up example is 20%. And so with Bayes' theorem, this is a way to answer questions that might otherwise seem very difficult to get to. My friend tells me they had a dessert. What are the odds? Another place where something like this might be used would be maybe like A/B testing. I give you one version of a website, I give somebody else a different version of the website, and we get a sense of if they picked something here, what is the chance they were using this version of the website? If they bought a thing or they clicked on an ad, what is the probability that they were looking at a particular type of ad? So here's an exercise for you folks. I give you basically the same 3 types of data. Sketch out your little probability tree. Start to fill out the tree until you have all the values populated. And then, much like we did up here, go ahead and work out those 6 items in the formula and answer the question. After some of my friends played 2 different versions of a board game, talking to my friend, the friend said, hey, I really want to buy this game. What is the probability that that tester played version B of the game versus version A? I'll give you guys a few minutes to go through that. Give you about 7, 8 minutes. All right. Oh my gosh. just finished. Put your little green stickies up. You're struggling, you put the red sticky up too. That's the thing. And even if you're not struggling, you just have a question. That's awesome. Any other question? All right, folks. We are coming to the end of the day. Okay. The big sticking point here is figuring out what each of these things are. Just as I kind of walked around and talked to a couple people and listened to some of the comments, right? The process of getting from point A to point B is essentially the hard part. And how this will normally play out in these types of examples. You will potentially be given one of these two values on a branch, so you have to do the math to get the other. You'll be given two values here, and you can get the third. You'll be given two values here, and you need to get the middle one, those kinds of things. And so as you get practice, and you get practice by doing, right? You do this over and over again. You will grow accustomed to, oh, I've got these 3 facts or these 4 facts, and I can start to fill in. And then once you get this down and things are working out really well, then you can start to apply this to real-world problems. Okay? But once this chart is filled in, the next step becomes take each one of those things, put them into the 6 spots, and then the math should theoretically work out. All right. I'm going to let you guys read this section on independent events, and we're going to move on to lesson 3 in the interest of time. So you guys can go back and read that on your own. We want to look really quickly at what we call discrete probability distributions. And then we want to understand a little bit about factorials, permutations and combinations, and what those are for and what they mean. In the middle of this, we're going to do a field trip. I'm going to take you guys out onto the wild, wild internets, and we will look at some things that are out there that might be of interest and use to you. And we'll talk a little bit about how this discrete probability distribution can apply to other things. But let's get started with the discrete probability distribution. One of the kind of the classic, I guess, examples of a discrete probability distribution is related to slot machines. By discrete, we mean it's broken up into individual components as opposed to like a nice curve, right? With this slot machine example, I have 3 slot machine wheels. Every wheel has certain symbols on it. It might have an apple, it might have an orange, it might have a quarter, it might have other random things. Depending on how the slot machine plays out, if I were to get an A, an A, an A, an apple, an apple, an apple on the 3 wheels, I get $4. I had to pay 20 cents to play, so my gain is going to be $3.80. If I got an apple, apple, orange, they give me $3, but again, I paid 20 cents to play, so I really only gained $2.80. Orange, 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 I get $2. I want to highlight this bit. This apple, apple, orange is any order. If I got an apple, an orange, and an apple, that still qualifies. I still get my $3. Woohoo. All right, they're still ripping me off. Okay. Now, on any given wheel, I have a certain number of oranges, I have a certain number of apples, a certain number of quarters and stuff on that wheel. And the probability of getting an apple is 1 in 10. The probability of getting an orange on a single wheel is going to be 2 out of 10. Probability of getting a quarter is 2 out of 10. And all the other symbols, the cruft, that's 50% probability of getting some other random symbol. Okay. What I'm going to start doing here is I'm going to start building out a table of details. I'm going to go kind of step by step building out the table. And it's going to take me to a point where I can figure out what is my average win at the casino. Air quoting the word win. What is my average loss at the casino? So here are my wheels. Here's how much they pay. Here's how much I get or how much I pay. So normally, when I screw up and I get nothing, none of the wheels helps me, I'm going to immediately lose 20 cents. If I get 3 quarters, I get back 80 cents because I've spent 20 to get there. We know the probability of getting an orange. So 2% or 20% probability of getting an orange, 20% probability of getting another one, 20% probability of getting a third. The chances of me getting 3 oranges in a row is 8 out of 1,000. Similarly, I can do the math to figure out what is the probability of getting all apples. That's 1 in 1,000. Probability of getting all quarters is 8 out of 1,000. And the probability of being a sucker is 997 times out of 1,000 I lose cash, straight up. All right, if you are a gambling aficionado, please don't be insulted when I say sucker. That's a colloquialism. All right. So, if I translate gains and losses, we can assign a probability of getting any specific gain. And here, I'm going to stop calling them gains and losses. I'm going to say X. So I have a capital X and a lowercase x. X is this random variable. And the little x is any individual item. And I've only got 4 or 5 options here. So out of these 5 options that fall into this big random variable. And so I know the probability of getting any of those 5 options, and I know how much money I get And that's going to help me figure out my average win or loss. All right. In our previous discussions, we talked about averages. We used the word mean. When we talk about these distributions, we use the phrase expectation. Little mood lighting. Sweet. Is somebody leaning on a light switch? All right. It was getting crazy cozy in here. All right. So, given any particular trial, I might lose, I might win. Is there a way to figure out my average? And that is using expectation. To figure out our expectation, we use a formula much like we had before. We say, all right, if I have a particular x, what is the probability that I'll get that x? And then let me add up all of those. And that will give me my mean. Ex is called expectation, but we also often call it mean, so you'll run into it as both. And matter of fact, we might use the symbol for mean, which is this, this Greek mu. All right. So for starters, I multiply the probability times the value of the variable, and I get these results. A bunch of them come out positive, and then we have this suckers category, which comes out very negative. And if I do all the math and I add all 5 of those results up, my average loss every single time I play this game, if I played it a lot of times, my average loss will be 16 cents every time I play this game. All right. Sure, I might win $4 once in a while, but on average, I'll lose 16 cents every time I play. All right. Now, knowing the mean is kind of cool, but we also often want to know how broad that spectrum is. Is there a possibility I might have a really broad spectrum and maybe I'll get really lucky on one end of the spectrum? To solve that, we essentially solve for variance. Right? So the variance of any given probability distribution is the expectation of the value minus the average squared. Right? So let's get in here. This is essentially the same chart we had before, but I take the value minus the average. Remember, the average was negative. I'm losing money on this, so I subtract a negative value, and I get this. Right? Once I have taken the average and subtracted from all 5 values, I'm going to have to go back and square it. So we jump in here. We take each of those values we just calculated a second ago. We go ahead and square them all. And once we have a square, we multiply it by the probability, and we get all these things. Again, you'll go back, reread this, kind of absorb it, take your time. But ultimately, once I've multiplied the square value times the probability, I can get a variance. And I can tell with this particular data set, it's wide, it's narrow, things are really close to the mean a lot of the times, things are far away from the mean a lot of times. But again, variance is such an ugly number. Nobody likes variance. So we have standard deviation, and that's just the square root of the variance. All right. So your first question might be, holy cow, how do we write code that does all of that? Well, we're not going to. We're going to skip that part, right? And we're going to go on a field trip. We're going to look at some libraries. These are your takeaways. These are things you can go home and play with and explore and consider. We're going to look at a couple of libraries and figure out how the pros have put these things together for our use. The first place we're going to start is the stats field trip. And for your reference, don't try to read out the URL, because that's just going to blind your eyes. All of these are linked at the bottom. And so I have all the URLs to get to each of these down at the bottom. Okay, so let's start with the SciPy stats library. Load this up a bit. Okay. Blah, 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 blah. The SciPy library itself has some tutorials that will kind of walk you through a series of things, certain basic functions they might have, or statistical functions that are present, etc. I'm going to dive into the scipy.stats library. I'm basically going to kind of scroll through this and point out a few things. The nuance here that I want you to walk away with is there's a heck of a lot of good work that's been put into solving some of these statistical problems that I should take advantage of instead of using Chalmers' crappy code. All right. We mentioned a minute ago discrete probability distributions where things take certain values. a $3.80 return, a $2.80 return. Well, there's other distributions called continuous. And so I'm going to kind of scroll through this. Right? They're all alphabetical order, A, so we got alpha, arcsine, da-da-da. These are all continuous distributions, and a lot of work has been done to try and create these objects in Python that you can use to look at distributions of data in various ways. And we'll dive in on one of these in a few moments. But there's a lot, right? So when we talk about you starting your statistics journey, this is step one. This is the first 3 hours or something of a 40-hour college class on intro to stats. And this is, you know, graduate level, whatever, right? But there is a destination you can get to. And in many cases, you don't have to go all the way. You don't have to know and memorize every one of these. None of us have that memorized. We build on the basics. And then when we need something particular, we go and try and hunt down the thing that will help us. We have what's called multivariate distributions that look at various types of multiple variables that correlate with things. We have some discrete distributions, which is what we were looking at a moment ago. And there's various ways to handle particular types of discrete distributions. And then, of course, they've got a whole slew of statistical functions, like mode and calculating for skew and for variation and standard deviation, etc. So let's go dive in on one of these. This is in the stats library, and this is related to a particular discrete random variable. It's called the binomial discrete random variable. And the way to calculate certain values that come out of this, they have this really funky formula, and we're not going to spell that out. I'll let you guys figure it out. But you provide it with a couple of values, and it will allow you to build kind of this body of information that you can then go and explore. And your exploration might lead you to making graphs that kind of show patterns in the behavior. And if you want to know specific details about the data that you could use to make that graph, they have a whole slew of additional kind of nested functions that allow you to dig right into that distribution and understand more about it, etc. Right? I'm not going to walk you through all these things, but they're there. So that's the first part of the field trip, SciPy stats. The next part of the field trip, we mentioned a library called NumPy. NumPy's got, much like the SciPy library, an incredible set of documentation where you can start to dive into particular things that interest you. And we're not going to explore this one the way we did SciPy stats. Pandas also has, again, kind of this incredible wealth of information about how you can calculate information using data. The Python statistics library, a couple of us were looking at this a few minutes ago. There's really only about 10 or 12 different types of functions here. This is more the meat and potatoes kind of things that you're most regularly and frequently might use. This does not get into any of the details like SciPy stats and NumPy and stuff will allow you. But it's there, and you don't have to import it. You don't have the weight of importing a lot of things from third-party libraries. So this is still useful for the things that show up most frequently. All right. So with that, so that was our field trip. I mentioned this idea of these discrete probability distributions. You go home, you start to wrap your head around that. One of the really cool things that you can do once you have a good understanding of a discrete probability distribution is that you can apply what we call transforms. In order to get to kind of this point, I had to multiply certain things by, hey, this is the probability that something's going to happen, or this is the gains and the losses, etc. Well, what if my slot machine owner says, hey, we're going to upgrade your slot machine, and it's no longer going to be $4 if you win this, but everything is going to be increased by a quarter. You'll earn $4 and a quarter, $3 and a quarter. Instead of having to go back and redo this, these transforms will allow me, if you guys study up on this, to very simply reevaluate what my variance is without having to do a lot of crazy math. So that's pretty cool. So you want to research transforms on discrete probability functions. So we got 10 minutes. I'm going to walk you through combinations and permutations with a sprinkling of factorials. If you recall, a few minutes ago, I said, hey, look at this. If I get an apple, and an orange, I'm going to win something. but I also illuminated the fact that it really, really wasn't just apple, apple, orange. It was any order of apple, apple, orange. So I can get an orange, and then an apple on the second wheel, apple on the third wheel. And when I calculated the probabilities for this, I took that into account. If I got apple, apple, orange, plus apple, orange, apple, plus orange, apple, apple, say that 3 times quickly. This was easy because there was only 3 things. I only had like kind of 3 combinations of this, or 3 arrangements of it, sorry. That's probably a better term. But what if I had lots of things and I had all sorts of arrangements? Is there a way to do that mathematically and do it easier? That's where factorials, combinations, and permutations come into play. All right. We'll start off with factorials. You might have seen this button on your calculator, never known what it does. There's often on calculators a button that'll have something like X with an exclamation or an N with an exclamation. That represents a factorial. And what a factorial is simply, I will take whatever number you give me and multiply it by all the things that are decremented down by 1s. So a 2 factorial is 2 times 1. A 4 factorial is 4 times 3 times 2 times 1. 10 factorial is spelled out. It's a nice way of very simply creating very large numbers that are composed of things. You might say, well, what kind of use would this be? Let's say that I have 4 books, for example, and I want to put them on my bookshelf, and I'm kind of particular about what order I put them in. With the 4 books in my hand, I could pick my first book. I have 4 choices, and I throw the first book down. How many choices do I now have left in my hand? I have 4 books to start with, and I put one on the shelf. How many choices do I have left? How many books do I have left in my hand? 3. So now I pick one out of the 3, and I put that on there. How many choices do I have left in my hand? 2, right? So these factorials are often used in these kind of things where you need to organize and arrange things. If I have a bunch of horses, and they're in a horse race. And by the way, Chalmer's not a gambler, but yes, say I have horses, and they're in a horse race. I have 20 horses. Which horse could come first? I have 20 options. Which horse could then come in second? I only have 19 options. Which horse could come in third? I only have 18 more options, right? So that's where factorials come into play. A great thing about factorials is that if I have to do division of one factorial by another, it's pretty easy because 3 times 2 times 1 over 3 times 2, these cross out, and I'm just left with 5 times 4. So it makes the math pretty straightforward. I've got a little function here. We'll calculate this, calculate that. And so I'll let you figure out the details of the function. But I've got a function that will calculate factorials for us. I want to highlight in vivid terms what I meant by Chalmers code sucks and other code is better by looking at a real-world solution. The calculation of factorials looks like it's pretty straightforward. But there is a lot going on under the hood. For example, if you're on a 32-bit piece of hardware, the size of an integer maxes out at about 12 factorial. If you're on 64-bit hardware, it maxes out around 20 factorial. Maybe your computer might want to build or calculate something larger than that. So you might use floating point approximations or representations of those values, and that'll nudge you a little bit past those points. Or maybe, in terms of speed, you don't want to calculate 40 times 39 times 38. You might want to have a lookup table for certain low-level factorials and then do the calculations on higher ones. Or you may not want to do the calculations at all, so you might use an approximation like Stirling's formula to figure this out. So real-world functions, not Chalmers, will do things to help improve the speed or the reliability of it. And I just want to show you what we mean by the speed of it. So I created a factorial function. We just looked at it a second ago. But there is actually in Python's math library a function called factorial. And I'm going to import it as f so that the 2 names don't override each other. And if I calculate the factorial of 4, it's going to give me back some number. And so let's go look at that, make sure we get something back. We get 24. Returns 24 as expected. There we go. If you've never used Jupyter to do this, it's kind of fun. There is the ability to time certain statements or expressions, etc., in Python. So I'm going to say use Chalmers factorial function and calculate 40 factorial and time it and show us how long it takes to do this. And then we'll use the library or the function in the math library, and we'll see how well it works. So we'll run that. The time it function's kind of cool. It will run this multiple times, and every time it runs it, it will do it some number of times, like 100,000 times. So it took about 7 microseconds to do it with Chalmers' crappy homegrown code. And it took 300 nanoseconds to do it with legit code that is really good at this and optimized for this, right? That is a massive difference. It's like 1,000 times difference, right? Something like that. Or 10 times difference, whatever it is. Math is not my thing. Don't trust me for your maths. All right. 3 minutes to go. Good grief. We'll talk about permutations, combinations, and products. With permutations, we will look at how we can arrange things. For example, how many ways can I arrange 4 out of 5 books on my shelf? Got 5 books, I only have room for 4. Let me figure out which 4 I want to pick. Or if I know that I care about 3 of the 10 horses that win, because I'm going to bet on 3 of them, how many different options are there that 3 will cross the finish line, right? Combinations, on the other hand, are things where we don't have to worry about the order of them. With the horses, right? If Sally Blue finishes in front of Denver Dan versus Denver Dan finishing first, the order was crazy important with that permutation. But with combinations, order doesn't matter. What did you have in your salad? I had walnuts, I had romaine lettuce, maybe I didn't, I had iceberg, I had croutons. The order doesn't matter. If I said croutons and iceberg lettuce, it doesn't matter. Products are a lot like permutations, but you not only care about the order, but you start to replace things. So for example, I pull a ball out of a lottery cage, I read the ball, I throw the ball back in, and I have the chance of pulling that same ball out again. But the order of the numbers matters. And then combinations with replacements, it's the same as combinations, but I put stuff back in the pool. So I've got a handy little chart here. Do I replace stuff? Yes or no? With those books, I couldn't replace them because I only have 1 copy of each book. With the lottery balls, I could put the lottery ball back in the bucket, right? Order matters, order doesn't matter. Right? So we can calculate permutations, combinations, products, and stuff. One thing that I'll leave you guys with, and then we're pretty much done. Again, rolling your own, not so good. There is a library called itertools that has a function built in to do each of these. And real quick, we'll look. I have 3 things. I want to figure out kind of groupings or arrangements of them 2 at a time. Right? When order doesn't matter, I only have 3 possible arrangements. But if order does matter, did 1 come before 2, or did 2 come in front of 1, etc. All right, we'll skip all of that. There we go. And those are the links to all the libraries. You folks have been amazingly patient through the day. Brains are all fried by now, I'm sure. I'm glad you came. I appreciate any feedback. I will get a survey link up on the screen here. I urge you to go to this particular location and give me feedback, because feedback is something that I need. So let's see. www.surveymonkey.com. And if I remember right, I think SurveyMonkey is done in Python. All right. And this is a capital HK 8268. Let me make sure I got this right. SurveyMonkey.com/R HGK8268. All right. If you guys need to get a hold of me, I've sent you guys some emails, and they have like my Twitter handle in them. You can reach out to me that way. My email is there. You can reach out to me if you want to ask questions. Please, please fill out the survey. That'll help me be better. And I appreciate your time. Glad you came. Thank you.